This one,
Yes.
PAGT.
Yeah. Forces and motion basics.
This one right here.
Yes.
Okay, so did you play this?
Not yet.
Okay, I mean that would be a good place to start. Are you still seeing the window? Because the new window popped up. Okay.
No, wait, I'm not seeing the new window.
Choose the 200 kilogram refrigerator. Okay. Let me do a new share. Okay, so you're seeing this now, hopefully. Motion. All right, so choose the refrigerator, I guess. Set the applied force to 400 newtons. Okay, to the right. Be sure friction is turned off. Friction, I don't see an option for that. Do you see an option for friction? Jack, you there?
Oh, wait, my mic was muted. Yes, I do not see a friction thing.
Okay, so this thing, it's moving and it just moves forever. Okay, what is the net force acting on the refrigerator? It's 400 newtons directed to the right. So let me do a new share. Let me make sure I'm sharing the entire screen, because I think that will help here. So you see how this refrigerator is just moving to the right?
Yes.
All right. I don't know what, maybe, I don't know. So it's gonna keep until I apply a force backwards. It's not gonna stop.
Yeah.
Okay.
And that's the idea. That's what friction does,
okay,
right?
So
it slows it down.
Its magnitude of the net force is 400 newtons directed to the right.
Yes.
So, is there any? So I don't know. Is it okay if I click on submit?
Yeah.
Okay.
Yes.
All right. Correct. What is the acceleration of the refrigerator 4 seconds after the person begins pushing on it with a force of 400 newtons? So the force is equal to mass times acceleration.
Yes.
F equals ma. What is the force? It's 400. What is the acceleration? That's what we're trying to find. Do we know the mass? The mass is 200. So it's 400. This is where this doesn't really work. This format doesn't work great. But let me. It's 2.
So it's 4. So it turns into 400 times 200 divided by something else. Divided by 60.
Let me share do a new share here. Okay. So we have F equals ma. The force is 400. The mass is 200, and we're solving for a.
Yeah.
So a equals 2. Is that okay? Is that clear?
That is okay. Yes.
All right. Okay. Part C. Adjust the mass of the refrigerator. So let me do a new share. Screen 1. New share. Okay. It says adjust the mass of the refrigerator by stacking different objects on top of it. If the mass of the refrigerator is increased, what happens to the acceleration? So we actually don't need to do this, but I don't. Maybe we can't. I don't even know if you can see this or not.
I can see it.
Well, if mass goes up, like.
Does the acceleration go up or does it go down?
Well, you got to see the equation to like understand. So let me go back to this. So if just pick up, okay, let's say the mass is now 400. What's the acceleration? Acceleration is 1 meters per second squared.
Oh, okay.
So it goes down. So when you hold force constant, okay, if mass increases, then acceleration decreases. If acceleration increases, that means mass must have decreased.
Okay.
So I'm going to go back here, and the acceleration decreases. All right. Okay, so I got to do another new share. Let me go screen one, new share. Okay. It says click the reset button and adjust the friction back to none with the 50 kilogram crate. So I don't know. Oh, there's the reset. That's the reset. All right. Masses, speed. That's interesting. Okay. And adjust the friction back to none. I still don't see anywhere for friction. Oh, there's one for friction. Okay. So there's none,
Okay.
I guess. Okay. All right. So there's friction back to none. With the 50 kilograms crate selected, that must be that one. Use the slider to apply a force of about 100 newtons. After 3 seconds have elapsed, release the slider so the applied force is now zero, and the feed is staying still. What happens to the grate after the applied force goes to zero? So we're going to apply a force of about 100 for 1, 2, 3 seconds. With no friction, the crate just goes forever.
Yeah, of course.
That's 1 of Newton's. The crates moves at constant speed for a while and then slows down, eventually comes to rest. I don't know if it will come to rest with no friction. The acceleration becomes zero and its velocity remains constant because it's just going to keep going, keep going, keep going.
How does the acceleration become zero?
It's zero because it's neither increasing or decreasing speed.
Oh, so it's just kind of like throwing something in space where it just keeps going.
Yes. So this is very conceptual.
Alrighty. So it's the first option, right?
Yeah.
Okay.
First option. Sorry. No, when I actually gotta do this. Okay. Click on the crate to bring it to a stop. Then replace it with the refrigerator. How much more do you want me to go through this? Because again, like I think maybe if you didn't know how to use this, you would, this is the friction one, this is motion, this is acceleration.
I think it's fine if I take over with it.
Okay. What should we go back to? All right. So we're on 5 of 15. Go to the next item now. Okay. Okay. I mean, is this what you want us to go through, or is there?
Yes, of course.
Okay. When two objects slide against one another, which of the following statements about the force of friction between them is true? The magnitude of the friction force is always equal to mu kn. It's always less than mu kn. Can be either equal to or less than mu kn. I mean, this is purely a definition. So other than me like giving you the answer, I'm not sure how I'm helping you here. Because the answer is the last one. The friction force is as big as it needs to be, meaning like it doesn't have to be any bigger than it has to be.
Say it one more time.
The friction force is only as big as it needs to be. So it doesn't have to get bigger than that, which is sorry, it's a very difficult concept to explain without putting it into an equation. It's kind of like the normal force. So the normal force pushes up on like imagine there's something on your table, like a book. The normal force pushing up on your book is whatever it is. Okay. If you
Mhm.
push down on the table, there's the same normal force,
That's going back at it to keep you
but it's
from destroying. Yeah.
but it's bigger. It's bigger this time because that book
Mhm.
isn't as heavy as you pushing down on your hand.
So the magnitude of the frictional force is determined by other forces on the
Yeah,
object, so it could be either equal
yeah.
or less than. Okay.
Oh gosh, did you log in? Because
Yeah, I did.
okay, that's why it didn't allow me to save that.
Sorry
So
about that.
what do you want to do here? Do you want me to keep going through this, or do you want to send pictures, or what do you want to do?
I'd like to send pictures.
Okay,
Could do that.
all right.
All right. Okay, so magnitude of the friction is determined by. Wait, it says that's incorrect. The magnitude of frictional force is always less than UKN, or is it always equal? Wait, I think it would be equal, wouldn't it? Oh, it's correct. It's oh. The answer is the magnitude of the frictional force is always equal to UKN. I'll send you a picture. All right, here are the last few. It should send very briefly. All right, when two objects are in contact with no relative motion, which of the following statement about frictional force between them is true? The magnitude of the friction.
Did you send this by email?
No, I sent it by text message. Should I do it by email?
Yeah, by email, please. Because
Okay.
I'll just forward it to my email.
Okay. I'll send it to you. All right. I got math.matthew.com. Um, all right. Should have sent.
All right. So you got. You said that part A, the magnet is always equal to mu kn. All right. So
Yeah.
part B, when two objects are in contact with no relative motion, which of the following statements is true about the frictional force between them? Well, if they're not moving, it's because well, there's a lot of reasons I guess they could be not moving. I'm going to say that's probably C, which is why they're not moving, or it's A again.
They're in contact with no relative motion. What does that mean?
It means they're touching, but they're not, and they're like kind of stuck together. They're not moving relative to each other, like you sitting in your car, in your seat. Like you guys, the seat and you are not moving together.
Yeah, I would C. Because for static friction, the actual magnitude of the friction force is such that together with any forces present will cause the object to have zero acceleration. The magnitude of the force due to static friction cannot, however, exceed UKN. If the magnitude of static friction needed to keep the acceleration equal to zero exceeds UKN, then the object will slide and will be subject to the force of kinetic friction. You're not on. Okay. All right. On to C.
just reading it. I mean, these are pretty tough for me to even answer because they're they're very conceptual. Friction's such a challenging thing in physics. Um, are you seeing my screen right now?
I'm not.
You're not. I don't understand that. Okay, there's this like graph of friction, which it's like you have to apply enough friction to get something moving, but then you don't have to apply enough to keep it moving.
Okay.
So there's this sort of like like point where it starts moving.
Okay.
So I don't know if that helps to answer this. I mean, to me, some of them sound more right than others. The coefficient of kinetic friction is not less than, it's actually greater than static friction because you have to get it moving.
Okay. I typed in the answer as something like the coefficient of friction. Wait,
So
yeah,
once
it
the
was
box is moving, when the box is stationary, W equals the force of static friction. Reduce it to the normal force, which in turn reduces the friction. W is greater, static, but less than the force. I want to say it's C, but it's still kind of a guess.
the correct answer is A for this. The coefficient of
Kinetic
kinetic
for
friction is less than the
yeah,
coefficient of static
yeah,
friction.
because this is all when this region is where it's not moving.
Mm-hmm.
So once it gets moving, it's the friction is less.
Oh, okay. All right then. Let's go to. I sent you pictures for page 7 of this. It's called tension in a massless rope. To understand the concept of tension.
So there's always a figure. Oh, there it is. Figure. Okay. Figure there. All right. What is the magnitude of the downward force on section A? Um, and you got to write in an equation, I guess, there.
Okay. I sent you another screenshot in your email of parts C, D, E, and F.
Okay. The free body diagram here is that you've probably heard that in class. You have FB going up,
Mm-hmm.
and it's what I'm not sure is are they differentiating between F FBU? What is FBU? Idea the downward force on section A. See they're saying the rope is massless, so it's the force that's pulling down on it is going opposing the force that's going up on it.
Mm-hmm.
Um, so I okay. There's more to it here. All of these questions are in Chegg, which I don't know how familiar you are with that. And sometimes
Yeah.
I just don't know what to tell you to put here because the answer is like F B C or F D, and I don't know. Um, and you got to enter it correctly. Like you got to write FB underscore C to get it to take. So FBU, FBTU. See, I don't know where. I guess they're going. I'm sorry. It's just because there's so much here. I'm not sure what to tell you. A to D. Why is it? What is the magnitude FAD of the downward force in section A? Yeah, I can't even tell you what to put here.
Section. So we have FAD.
It would normally be mass times gravity, but it's not because I don't think that's what they're looking for. I can punch this in. I mean, I can tell you what the answer is. I'm having difficulty trying to explain why it would be the answer. So let me pull something up here. Sorry, Jack. I mean, this format isn't great for what we're trying to do here. These problems are not the easiest to explain in this format.
It's okay.
All right, so I pulled up the problem on Chegg. Let's see what it says here. Why didn't it just come on? So they say it's just T1 because there's a I guess they're referring to the tension
The
that's at
tension.
so it's T_1. Okay, I now I see. Express your answer in terms of the tension T1. Okay, well that makes sense. So it's T1. The tension from B to U, and I don't really know what that I mean, I guess. Okay, they're trying to say that the tension is the same in all places in the rope.
Okay.
And that's why part B is also T1.
And it's what's the difference between what's the upward force and then the downward force?
Which one are we asking about here?
Part A.
Well, it's the downward force is T1. So it's just T1.
That's it. T1. All right. All right. Let's see if I can.
And make sure it's T_1.
T_? Okay.
Yeah.
T_1. All right. Okay, so that's correct. All right. What is the magnitude? So we got T1 going down, and then we got for FBU. What's FBU mean?
I think it's the tension from force B to U, the point B in the rope.
How do you know what a magnitude is? I don't understand that concept.
It just means it's without direction. So you're like when you're driving your car, you have a speed like 40 miles per hour. It doesn't matter whether you're going north or south. It's always 40 miles per hour. It's already got the magnitude built in to it. Like you don't have to adjust for sign. It's not positive or negative. I believe the answer is also T1 for part B.
Yeah, I think that's the only thing that makes sense in this case. And that's correct. All right. So the magnitude of the upward force on FCU, and the magnitude of the downward force on FBD are equal because of which of Newton's laws?
Yeah. So I actually need to look up the Newton's laws to be able to tell you. It's just mean that it's the equal and opposite law. I think that's the third law, but let me look. Yeah, it's the third law.
Okay. A body will emit. All right. So two exert a force on one another. The forces are equal in magnitude but opposite in direction.
Yeah.
Okay. All right. So now we go down to D. The magnitude of the force FBU is what? FB. Oh, right. So the magnitude of FBU It should be equal to FBD, right?
I gotta pull a picture back up. Sorry. You're up to
Part D.
FBU, and FBD. Well, yeah, they're equal or equal and opposite or something like that. Oh, the magnitude, they should be equal. Yeah.
Yeah, and that's what the third law exactly states, is that they'll be equal, right?
Yes.
All right, so now part E. Now consider the forces on the ends of the rope. What is the relationship between the magnitudes of these two forces? Now consider the forces.
They're also equal.
Yeah, there should be greater than or equal to.
No.
All right. Now that's correct. And part F, the ends of a massless rope are attached to two stationary objects, like two trees or two cars, so that the rope makes a straight line. For the situation, which of the following statements is true? Tension in the rope is everywhere the same. It's the same everywhere, but okay.
I believe that's true. The
Mhm.
magnitude of the forces exerted on the two objects are the same. It's true. And
Okay. Wait, must be in opposite direction. If two bodies exert a force on one another, the forces are equal in magnitude but opposite in direction. So it should be true, right?
Yep.
And the last one is false. The force exerted on the two objects by the rope must be in the direction of the rope. That doesn't work. What? Oh, I got that.
It just means it's like moving in that direction, meaning like they're not like perpendicular to the rope. They're going up and down it.
The tension of the rope is everywhere the same. That should be true, right?
Yeah, I think the first three are true and the last one is false. These are tough because they end up giving you partial credit if you don't get them all right.
I clicked the first three, but it was wrong.
Yeah.
The magnitudes of the forces should be the same.
It does give you. It almost always gives you a hint that may or may not be relevant.
Let's see. Is there
the other thing here is it's part 5. It's the fifth part of this, so I wouldn't. You can move on, or it's not a big deal here to move past this.
Oh, they're all true? Oh, they all are true. That's odd. So it must be an wait. So the forces exerted on the two objects of the rope by the rope must be in the direction of the rope. What does that mean?
Like if I think you're still seeing my screen. If this is the rope, they have to go this like up and down. They can't go to the right or to the left.
Okay, so it must be in the direction of the rope.
Yes.
So it's both like kind of going in, I guess.
It just means that they're going. If the rope is going up and down, then the forces are going up and down.
Okay, all right, that makes sense.
Not side to side, for example.
Mm-hmm. All right, I'm gonna screenshot this for you, and I'll send it to you. All right, so we got this. Then we got this. Where did I get that? That's the second one. All right, let's just send in just a few seconds on your end.
All right, 2 blocks with masses M. Is that the one we're looking at?
Yes.
Okay. All right, so I'm going to do what I should have done before, which is snip these in. That'll potentially help here. And then we got the figure.
All right, so
Okay.
first one, find T2, the tension in the lower rope. Express your answer in terms of some of the variables.
Yeah, so this is you got to look at you got to sort of like what I do is draw these sort of cuts of the pictures. Is the if you look at just M1, it has T1 going up, and you need to figure out what's going down. Well, it's mg is going down, okay? But
Okay.
m is generic, like it refers to whatever it is. So in this case, T1 minus big M1g equals 0, because we're choosing up to be positive and down to be negative. So T1 equals M1g.
Minus mg?
Well, you can add this to the other side of the equation.
Oh, no,
Okay.
stupid.
Well, T2 is pointing up. Well, T2 is the rope. So
yeah.
if the rope, if pointing down on the rope is M1G and pointing up is T2, well, those have to be the same. We just learned that in the previous question.
Okay. To find T2, the tension in the lower rope. Is there like a number that I have to put in there?
It's all symbolic. That's why it says in terms of M1, M2, and G.
Oh, so this is just M1. M1G. 1G. This one says incorrect. The correct answer does not depend on M1. So it is G? No. The correct answer involves the variable M2, which was not part of your answer.
Oh, well, T2 is, I'm sorry. So T2 is just M, I guess, so they're just looking at this bottom part, I guess. So the T2 minus M2G equals 0 because it's not moving. So T2 equals M2G.
Okay.
So I think it means. And if that's
now
not
this one is asking for the upper rope for T1. Find the tension in the upper rope.
Talking about part A or part B?
Part B now.
Yeah, part B. So we just did part B. Part B is M1G.
All right. This is incorrect. Be sure to consider all the forces acting on the block.
So they're saying that it also depends on the. All right, so see, Jack. I mean, there's so much going on in this problem. It's like you're not going to learn this by this exercise here, because T1 is going up here on M1. Well, what's going down is T2.
Mm-hmm.
So there's two things here. There's minus M1G minus T2 equals 0. Well, T2 is, if you just look at this part of the drawing, we know that T2 minus M2G equals 0. So we need T2 equals M2G. So that means that this comes up here. So we have T1 minus M1G minus M2G equals 0. T1 equals M1G plus M2G.
Oh.
Because the block is it's adding to it.
Okay. All right, find T2, the tension in the lower rope. Okay. So we got M2 and T2. T2 is going up and wait, no.
We kind of already done T2. T2 is M2G.
M2G.
Oh no, but the blocks are not accelerating, so that's actually not right. There's more there's more happening here. Oh, there's always so much here. Okay. The blocks are now accelerating upward. All right, I got to snip this in. So there's a lot that leads into this. Like you're supposed to draw these free body diagrams. So T2, in terms of the variables M1, M2, A, and G. So T2 is here. You don't have to worry about what's going on above it. There's M2G down, but this thing is accelerating up. So acceleration is positive going up. So we have T2 up minus M2G down equals mass times acceleration. Well, the mass is M2 times acceleration. So the tension 2, if you solve for T2, T2 equals M2G plus M2A, because I'm just moving that to the other side.
All right, now for T1, find the tension in the upper rope. Express your answer in terms of some of the variables. All right. Do we do this acceleration thing with this one?
I don't have a picture for that, or I need to pull up. Find T1.
I sent you a screenshot for that.
Yeah, there it is for part D. Okay, let me snip that in. So find T1, the tension in the upper rope, if it's accelerating upwards. Now, so there's how do I say this? So we're looking at the whole thing now.
Yeah.
Okay, so we know that there's T1 up, but there's the M1 G down minus M1 G down, and then this rope here is pulling down, and that's T2. So T2 is also, I know it's pointing up, but it's pointing up from that one, but it's really pointing down from that. So it's minus T2 equals mass, the mass of this one times acceleration. Okay, but T2 we know down here when we looked at this before, T2 equals M2G.
All right.
So we have to substitute that out. So then we know that T1 minus M1G minus M2G equals M1A. So T1 equals M1G plus M2G plus M1A.
This one's all right. So M1G plus M2G plus M1A. This one says incorrect. Be sure to include all the forces acting on the block. What was the tension T2 expressed in terms of the given masses in G?
Well, okay, so it could be that there's a little bit more here to T2. So T2 minus M2G equals mass 2 times acceleration. Because they're moving together, the accelerations are the same in both of them. So we might have made a bad substitution for T2. Like T2 might be all of this, M2G plus M2A.
Mm-hmm.
So that would change this right here. This would be minus M2A here. And then this would be plus M2A here.
Oh, plus M2A.
Yeah, that might just do it.
Correct. I think that takes us into the lesson.
Right. Just yeah, I hope you got something out of this tonight. I apologize if it wasn't as good as usual, but
that's fine.
Still happy to help. I'll still send out the lesson notes and the screen sharing right away.
All right. Thank you.
All right. Thanks. See you, Jack.
Have a good day. Thank you.